Thank you very much, Antonio. Thank you very much, everyone, for inviting me and giving the opportunity to show a little bit what Hudson River Biotechnology is doing. As Holger is mentioned, we are a contradiction in the system. So we are a European-based gene editing company. So that sounds like a contradiction in itself. But we proved that it's possible to work in gene editing in Europe, though I have to say that our clients mostly are not in Europe. So, but that's something that I will explain during the talk. And I was given the chance to try to bring to this forum the view from the industry and a little bit about what we are doing in terms of the bridge between the plant breeding industry and the science that is behind genome editing. Quick facts on Hudson River Biotechnology. The two founders, they are two Dutch gentlemen. They met in New York, and while they were watching the Hudson River, they came up with the idea of why don't we apply genome editing in plants while we're back in the Netherlands. So they came up with this idea, and then they founded the company in 2015, and is based in Wageningen, in the Netherlands, very close where the university is, where it's very strategically positioned there, and it's mostly focused and basically only focused on gene editing in plants, so nothing else. And that gives us a very good position, and we've been ranked one of the most promising startups in 2019, and in the late polls about the CRISPR startups that really are going to impact in the biotech sector. We were one of the number 5, basically the only one in the agro sector. So we have a very prominent position, even though we are a relatively small company and it started not so long ago. And we, Hudson River, we deal with all kinds of customers within the agro sector, mostly seed companies. It goes from the large seed companies, the big breeding companies, but also with the small and medium-sized companies where we offer CRISPR end-to-end solutions. So we basically have all kinds of possibilities to do business. And we also have the ingredients and also pharmaceutical applications for biotech companies. Our mode of collaboration is, I would say, breeding projects. They come up with, we want to trade, how can you do that for us? Or for example, they have their own developments in-house and they would like to co-develop some certain parts of the R&D pipeline. And we establish even strategic partnerships for that. So we are very flexible to the type of interactions we have with different customers. But I think one of the things from the industry point of view is what we are seeing is that there is an enormous pressure from the society to change things, to transform agriculture, because there are so many things that needs to be addressed in the coming time. And we need to address it right away, and they're coming. It's happening right now. So the fact that we should do something quickly about it is something that for industry remains one of the driving forces to change things. We can talk about the growing population, the amount of people that is growing, and the food that these people will require, and the change of the habits of these people require more quality food. How are we going to secure that supply? That needs to be changed, of course. The pressure on the ecosystem, we need more food. Are we going to use more land for that? Hopefully not, because actually we are getting less arable land. And moreover, with the climate change, we see that there's predicted that 17% of the loss will be losses in the harvest due to the climate change. So how are we going to grow more with less in a more sustainable manner? Of course, the answer to all these questions, and in the industry is very clear, is about innovation in agriculture. Innovation is not something that came out of nowhere. Innovation in the agriculture has been done for many thousands of years through crop domestication, crossbreeding, and then many other different innovations that had happened along the years that have been used by the farmers at the end. And this is what we have right now in the supermarkets, is the product of that. And just to point a few examples of how domestication has changed the way of the food that we are eating, we have this classic example of maize, the first maize that there is there, the domesticated one, that is the one that we eat, has been changed to the process of selection of the farmers. These are the bananas that were, at the beginning were like this, full of seeds and very small, and now you have this Cavendish wonderful, that now they are threatened by the Panama disease. And this is something that only domestication has made now a staple of our diet. And the same goes for tomatoes. Tomatoes were like this, coming out from America, which were poisonous and full of hairs. And now you have these wonderful tomatoes. All this food that we have now in the supermarket is the product of human domestication, the selection from the farmers and now the breeders, trying to improve the varieties that we have. How they do it is a different story, but this is the product of that. And I think one of the key aspects is how innovation has been trying to minimize, for example, the impact and try to make it more cost efficient, the way that we are making our own food. And this is an example from how in the 1940s, for example, to get 250 kilos of corn, you will need all this field that you see on the right. And with the new selection, with the technologies that have been improving the corn, you can see that less and less field is needed, and now you have the very, very small amount of field. You have enough production of corn. These achievements can be only have been done because of the application of technology into plant breeding. And of course, the plant breeders have a lot of pressures when they are asked to create new varieties. They have to try to fulfill all these requirements at the same time, trying to go from, okay, well, now we have to have new varieties that are able to adapt to climate change. How are we going to reduce the environmental footprint, fertilizers, pesticides, and still being able to appeal to the consumer, no? for his preferences that they're becoming more and more outspoken about what do you want. You know? So all these things are in the mind of the breeders trying to create these new varieties. And maybe a good thing to recognize is try to understand what their challenges is to create these varieties for the breeders at the breeding companies. When they go to this, what they call this cycle of breeding cycle, in which they, in one way, they try to have enough variation, the genetic variation that Jorge was talking about. They have enough variation, and when they make crosses between the suitable parents, they end up with, after selection, to come out with the plants that they are more suitable for the trait of interest. And this selection basically decreases the genetic variation till there is a moment where you have a plant that goes for what they call the product development, and then finally is commercialized and go to the market. And this goes back into this cycle to increase variation. How do we do this increased variation? We can do it in many ways, like we are saying, the mutagenesis that we were talking about, genesis, epigenesis, all kinds of variation that can be introduced. Cross with maybe wild germ plants that you have around until you find again this cycle of cycling. But this comes with several problems that already Holger pointed out before. You have what they call these bottlenecks of genetic variation, in which you would like to basically capture some of the new traits that are out there, maybe in some wild crops or maybe in some other relatives that they are out there, and you would like to bring them into your elite varieties, the varieties that actually will end up in the supermarkets. And the problem there is that there is a very narrow genetic diversity there, and the possibilities to exchange material is rather complicated, because you have this narrow genetic diversity there. So the problem there is that they are facing with the limitations that come with this actually domestication and selection process. Of course, the industry has come up with all kinds of plethora of ways of overcoming these narrow genetic backgrounds. And how they do that, they came up with more than the conventional crosses to create variation within the different lines. You have the magic lines, you have the epiril lines, you have non-populations, all kinds of fancy ways of combining genetic material to create diversity. And that's the basis for later on crosses and later on developing new traits. Of course, now we have the speed breeding that allows you to have less cycles more cycles in the same amount of time, so you can generate more and more variation. This variation can grow faster, and you can have them earlier to be tested and find out whether you have the trait of interest or not. And all these revolution happening around the field plots, where you have all this equipment and the smart farming and all these digital technologies that they're coming to the help to find out what's going on in the terms of the phenotypes of the plants. And of course, you have the double haploids, all kinds of different tools that the breeders are now having at their disposal to make this breeding cycle faster and faster to basically meet the demands from the consumers. This is a typical breeding scheme, and it's a product development cycle, is called, in which is very important for the industry to people understand that there is a first phase in which you have the R&D section, which is trying to find out what are the causal genes for a particular trait. And that could be that you identify the gene, or you just have a region, a QTL region, defining where the causal gene is there, present or not. This takes a very long time until these causal genes are identified and move to the next level. Okay, now we know the gene. And once we know the gene, we apply traditional or molecular breeding methods to bring this particular gene or allele into the population. It takes a very long time, and we'll explain a little bit about it. And once you have it there, then you have to phenotype, you have to field test. It takes 1 to 5 years, and that goes to the market, and then finally to the supermarket. But these aspects, all of them, is the chain that is needed in order to, from the moment that you decide a trait is interesting for the market until you actually end up with a product. No? And of course, at the time of the moment that the genetics was coming into place, that we were having more and more knowledge, we are getting more information regarding the genomes. The industry was really taking this by the horns and say, how can we leverage all this information that has been accumulated in the literature for such a long time? How can we come up with understanding what is the traits and how the molecular mechanisms for these traits, and do I have in my germplasm valuable alleles that I can use to actually transform the rest of my elite varieties? And that's one of the main concerns and one of the things, the main driving activities from the R&D for the breeding companies. And because the moment they understand the presence of the gene, they can try to anticipate how the crosses will grow if you go for traditional crosses, and how the probability that you have linkage drag, or you have problems regarding the inversions happening in places where the gene is located in places that there are no exchange of material. These type of problems, they can actually face and understand them and put a solution if they have enough crosses, or they have enough populations or enough diversity in these populations. But this is the first step. The genomics introduces the precision breeding. But there are other problems, and the problems stem from the fact that plant breeders are working with the more horrible genomes on Earth. And that's the problem. So they are the biggest genomes. So they have the organisms on Earth with the biggest genomes out there, which means that they are more difficult to track when you are trying to get a homogeneous product in the market. You would like to have a very controlled genome. So you are talking about the biggest one, more difficult. Then the other aspect is that most of them is basically repetitive elements. And in some cases becomes really most of the sequence of the genome that you have out there. So when I was having hosting the genome facility, the point was that, okay, if you think about the genome, you try to reconstruct with sequencing like a puzzle, is basically when they're giving you this jigsaw puzzle. I mean, it's like most of it is basically the freaking sky, and only very small proportion of the reads become the genes, and so it's a very complicated puzzle that the plant genomes when you have to reconstruct them. And just to make things even more simpler, many of the crops that you are actually eating contain polyplication events, maybe the tetraploids, or you have hexaploids, or you have all kinds of ploidy effects that usually are sometimes associated with domestication. So the plant breeders are facing one of the most challenging tasks on the Earth, with the pressure on the society and the complexity from the organisms that they are dealing with. So they're in need of some help. And if you think about how they are doing right now, they're moving from traditional breeding towards molecular breeding. Many companies right now has adopted into the R&D pipeline as a way of finding out the causal genes. This is a typical molecular breeding, step by step. And one of the things I would like to point you out is that, the quicker the better. That's the rule for breeding, of course. But if you go to the scheme here on the bottom, even if you find out what is the gene, the causal gene, if you try to apply the the normal methods, the traditional methods, the methods that are actually allowed to have in Europe, for example, these crosses will have very different background, and then you have to make cycles and cycles of breeding until you end up with a trait of interest surrounded by the rest of the background that you are interested, because that's what you want, just the trait of interest. Maybe it's one gene, maybe it's a region of the genome, that's enough. When you want to bring the trait of interest, you have to clean, and this is a very important question, you have to clean the material from the rest of the red stuff and getting the rest of the back stuff, usually by crossing, but many of these times requires that the elite variety that you have, the black one, ends up doing some cycles, and this back crossing, it will take cycles and cycles, a lot of time until this is happening. And that's this 5-7 years minimum until you actually have the trait of interest introgressed into your varieties. And then comes the game changer. The game changer for agriculture comes when these two ladies end up with the Nobel Prize in 2020, already described by Holger very well. And I think one of the things that the chairman of the Nobel Prize Committee, this has revolutionized the molecular life science and all the levels, including plants. And one of the things that is important for the rest of the talk is what was mentioned before, is try to understand the differences in terms of what type of changes can be done, what kind of edits the technology can achieve, and which ones are the ones that have, the mechanisms are different. For example, SDN ones, the ones that basically the self repair machinery in the cell is making. So this is the one that you are not introducing any change, so it's change that happens by itself. Or if you are directing the change, the SDN2s, depending on the size of these changes, then you have SDN2s or you have SDN3s. So all these possibilities are out there. So why this is a change in the industry? In the industry, this is changing because now the cycle that you see on the bottom of is changing from all these crosses and all these extra cycles and all these years that you have to wait. Suddenly, the promise of the technology is that they can be skipped in just one cycle. And that is a tremendous promise. For you can introduce the trait of interest in just one cycle. And that product, hopefully, and this is one of the things that for us is a very important thing, that product that comes directly from there is ready for product development. And that's a major thing. So no cleaning up cycles. That would be fantastic because we're moving from this scheme that I was showing before, where in the lower panel you see traditional to molecular breeding 5 to 7 years. Suddenly the promise is that we poof a transformation pipeline, including gene editing, and suddenly that is reduced to half a year to 3 years. That is a major change. It's a very, very promising change. And that changes the way that, for example, maybe in the future, this is a little bit projecting of what we think is going to happen, not only at the consumer level, but also at the breeding companies, is how this is going to change. Is we now have the feeling, okay, what do we want? What is the breeding target? What is the market demanding? Or what will demand in the future? So now we move, instead of reacting, so maybe we can be proactive and finding out what will be the desired outcome, and now we can start working on the varieties that actually respond to these necessities in the market. So the only thing we have to do now is to design the novel genetics. Now we know which genes probably are involved in this particular trait, create the novel genetics through gene editing, for example, and now you have the plant. So this is the vision for the future. And we can start with very low-hanging fruits, like, for example, monogenic traits, where already a lot of information is known. For example, this is on the left, a very, very simple example. You have a tomato that, thanks to a lot of work in the literature, now we know the loci that is actually responsible for the disease. So we were talking about the MLOs, but we can talk about the MR6. We have many loci that are associated with resistance to diseases. So knocking them out will give you already a very known well phenotype. So why don't we start with them? We can actually start knocking out genes and providing resistances. You can, in the industry, we have a lot of R&D pipeline that has been developed for many decades already. The genes associated to particular traits, can we validate them using gene editing? Well, that's one of the things that you can do, because that we can do in Europe. We can actually, everything that is done in gene editing for R&D purposes is actually allowed. What you cannot do is the products that come out of that, you cannot put them in commercialization, fine. But actually they can use editing for R&D validation. But hopefully, and this is the future, it would be great if this product development can be done in the elite variety an elite material that is just one genome editing step away from that. So that will be fantastic. But this has to, it will take time until this gene that you have found in your R&D pipeline, or basically in the literature, all these efforts that have been made to find out the genes underlying the molecular mechanisms become the editing target. Because at the end of the day, gene editing is just a tool, like used to be PCR. It's just the only thing we need is to find out where to edit. If we don't know that, we are not gonna, that's useless. So it's just a tool, but it's a very, very important tool. And I think this is what I'm trying to say with this title. No? So gene editing stands on the shoulders of giants. Decades and decades of scientific work now pays off, because now can use all this information to actually identify genes that can be used for commercialization of novel gene editing crops. That is wonderful. So we go through the literature, we look at all the things that has been done for changing the levels of sugars, or the acidity of tomatoes, or the stem length on wheat, root architecture, or inflorescence. You tell me. The traits of interest are all out there. And there is a lot of information. So why don't we use editing to find out, to get a new product? And what we offer to our customers at Hudson River, for example, is what we call a trade catalog. So we tell them, what do you want? Because actually this is possible. If you can choose the gene of interest here, we can find out a way to provide you a plant with this, because the technology is available right now. So imagine the change of mentality that this is possible. You can choose the type of plants that you think in the market will be, and we will provide you the plants right away. And these products for us, when we see it from the industrial point of view, makes a lot of sense to use them commercially, because what we see is that if you compare, and I think Jorge already mentioned before, you compare the number of spontaneous mutations that you can get in normal crops, or just the introduced by mutagenesis, CRISPR is really finally targeted. It's like a sniper, directed the changes in the genome to something that we already know the effects on the homeostasis of the plant, and we know already the other pleiotropic effects that we can have. So actually we know everything because that has been documented in the literature before. So we are aware of the possible problems. What we don't know is what happens with these 600 or 3,000 different mutations that mutagenesis introduced randomly. That we don't know, do we? So finally, we have a tool that is leveraging science and knowledge, and actually directing to create new products facing the challenges from the society. And I think it's very well put in this graph here, that the ones on the left is the amount of off-target mutations that you get, not only the ones that you're interested in by mutagenesis, the ones that can be done by crosses, because you introduce a lot of foreign material there, and the ones that you're using gene editing. And that was this plot was at that time where off-target mutation was of concerns. Now, in the daily practice, we don't see off-target mutations. We test the regions that they are prone to have maybe off-target mutation. We don't see them. Actually, we are improving the tools to the point where even the off-target mutations are not detected. So it's difficult to understand how the regulation now is, okay, the first two ones are safe, but the dangerous one is the third one. Oh yeah, that's the dangerous one. Moreover, just to make it practical, I think Sigrid put it very well. The European network of GMO labs said, okay, technically it's not possible to distinguish genome editing changes from plants obtained through mutation breeding or a spontaneous mutation. So how are you going to enforce it? So you're leaving that responsibility to the companies now. Is that so? I think regulation should be doing this. A regulation, as responsible regulation, in which we all participate, because the industry is the first interested to change the consumer perception from this product. But just leaving to the market to decide what it is labeled and what is not labeled puts us in a very difficult situation. And as you say, consumer trust will be gone. But for the industry, what we are seeing now, the opportunities again, is that what I was telling you, now no more cycles and cycles of gene stacking, which takes years and years, pyramiding, traits, forget about it. So you have a technology now that allows you to have polygenic approaches. You can target these complex traits. Maybe you have many genes that they are associated. You know how to target them in just one round. One round of editing, you have it. And moreover, when you're talking about this wheat polyploids, you tell me it's an hexaploid. So you have to, if you want to knock out one gene, or you have to edit one gene, you have 6 alleles to deal with. Good luck if you try to do it with a normal breeding allele by allele. You tell me the amount of effort, cost effectiveness is not feasible. One round of editing. So I'm telling you, the question now is from the industry perspective, from the Hudson River, what we see now is that if we want to have CRISPR as a toolbox that is feeding plant breeding to make all these possibilities, introduce genetic diversity, causal genes, how to identify, break up their linkage, all these very wonderful things that we can do at plant breeding and produce the products in the market that the consumer is waiting for. We need the first part, which is develop the CRISPR toolbox in a way that actually, it can be used by basically anybody. And right now, what we have is the gene knockouts. In this case, we are using the SDN1 changes, and we just introduce basically an indel in the coding breeding, in the open reading frame of the gene of interest, and basically you have a knockout, and that is enough to have the phenotype of interest. Sometimes, and this is also what we are working on, is to identify gene regulatory elements that are associated with the expression of the gene. Sometimes you do not want to knock out the gene, you actually want the opposite effect, as it was mentioned for Zach Liebman in the tomato. So we look for these regulatory elements, and we knock out, basically we edit these regulatory elements, looking forward for the ones that are, for example, repressor elements. You knock out the repressor element and you have an expression that is increased for the gene of interest. And these type of elements still are SDN1s. The same goes for the targeted random mutagenesis, which is something that they was done on the promoter of the genes of interest, just to find out how to identify the gene regulatory elements. All of them, together with the gene stacking, are SDN1 approaches that you can do right now in many countries without any GM label. If you want to go to the next step, in which you actually want to change one single nucleotide, and for example, this is a very important case when you're talking about herbicide tolerance, in which you know the gene and you want to make it resistance, for example, to the herbicides, that requires a very point mutation. And for this, you have precise gene editing. And the HDR, as it was mentioned before, is still is ongoing, is getting better. The efficiencies are getting higher and higher, but it still is an ongoing situation. And moreover, I don't think there is much efforts going in this direction so far, because this belongs to the SDN2 type of edits, which right now they are not having traction in many countries around the world. So there is not a backup from the market right now. Can we start with the SDN1s that provides already a lot of traits of interest for the consumer? I think that's the way to start. And as I'm saying before, I think that they will have less resistance. But one of the reasons of existence of Hudson River is what we found out, like with many emergent technologies, that besides the regulation that of course is beyond our control, we found out that many breeding companies are not adopting gene editing as one of the major tools in their breeding programs. And this is a timeline for any emergent new technology. At the beginning, when I was telling you about, oh, this is wonderful, we can do all these things, we can say this all the time, we cannot be all these wonderful things are there. But why they are not adopting it? Why do you not see them having them incorporated? Because what we are now is what we call the trough of disillusionment. So many of the companies are like, yeah, it's not worth it. Yeah, we have to pay a lot of money to actually have it there. There is a very complicated landscape. I will talk about that. And to be honest, I do not see the benefit of that. There is some technical problems to adopt it, and legal problems, and besides the regulatory ones. And at Hudson River, basically, we identified these things when we were talking to the breeding companies, because the R&D managers were coming back to us and say, I have my breeding guys coming to me and say, what the heck is the advantage of using CRISPR compared to what I'm doing right now? Because with the CRISPR systems, and it was mentioned in one of the questions for Holger, is that in many cases, the conventional CRISPR approaches use integration of the editing machinery in the DNA of the plant of interest. And that is okay to have a production of the editing system out there and having the edit out there, but then you have to do the cleaning up again. So there at the end, how much time are you saving if you have this conventional CRISPR approach? Well, actually not that many. They're not saving too many months. So why to go for this very novel and fancy way of doing things where you will have the regulatory problems afterwards when you can have the traditional approach that basically is saving, you're just adding just one more cycle, 2 more cycles. And that was a very good question. And many breeding companies were reluctant to adopt it because of the conventional CRISPR approaches. So what we found at Hudson River Biotechnology was that if we want the plant breeding companies to adopt the technology, we have to increase the efficiency of editing. That's one of the aspects. I will talk briefly about the CRISPR licensing. All the CRISPRs are using nucleases. Depending on which nuclease you are using, you have a different IP surrounding it. If you are using Cas9, then you have to talk to the Broad Institute and the University of Berkeley and having all this legal department talking to them, and it's complicated. Or if you have Cas12, for example, you also have to deal with a complicated IP. So yeah, is there a work turn around that? And moreover, what they're asking you is usually, and this is usually the problem with these things, is that the same license that they're using Cas9, for example, for humans, for human therapy, or for biotech, is using for agro sector. So they're using the same business model, and sometimes it's really, really, really high prices. If you want to commercialize a product based on Cas9, you have to pay royalties, for example, an insane amount of royalties to the Broad Institute or the UC Berkeley. So that prevents, for example, the adoption, because then you will have a burden in your commercialization besides all the regulation part. The third aspect that we found most dramatic to change was how can you deal with integrate DNA from the agrobacterium or one of these vectors? How are you going to take it out? Well, cleaning up, making cycles and cycles of back crossing now, and taking a lot of time until you have a product that is ready for commercialization. Moreover, if you do not have the edit done in a very specific way, you will have cells with an edit, cells without edit. You will have a chimera. So how for my chimera you came up with a homogeneous plants that you can actually have in the supermarket, completely homogeneous? That's again rounds and rounds of cycling, cleaning up, a waste of time. And finally, how we're dealing with multi-targets and polyploids. So all these, in our case, we were working for a solution. We call it the Mad Tiger solution, the workflow, which we address all these things. And what it does is that from the conventional CRISPR approaches, we move to an approach which is, okay, you can give us the plant and we give you back the plant of interest with the edit change ready for commercialization in just one cycle. And that is the game changer for many of the plant industry, because what we offer is a transgene-free approach. So actually no integration whatsoever. This comes back to RMPs that Holger was talking about before. So actually we produce the protein, we produce the guides, we encapsulate them in nanoparticles, and these nanoparticles are basically introduced in the protoplast. The edit is happening there. So actually no integration of foreign DNA is happening. The second, we have our own proprietary guide software to optimize the efficiency, and we have chosen MAT7 as the nuclease of interest. MAT7 has a different IP landscape, way more friendly than any other choices that are out there, and basically we do not have ties with the Inscripta Institute, which is the provider of the MAT7, and we have the license for commercial and R&D purposes. So it's a much more friendly approach for the customer. And we have in our hands, because we have the same problems that Jorge was saying with using nucleases from the human field, is that how to work with plants. Now we are, after years of working with MAT7, now we are reaching efficiencies that go above 40 in the protoplast assays, which is always less than the actual technical efficiency. And I think the final aspect that we were working very hard is to find out a single cell regeneration protocol, in which you would basically regenerate from a single protoplast with the edit of interest, the full plant. And then you know that you have, at the end, a homozygous plant with a single of multiple gene edits in just one round. And the timeline for all these things in several species in which we already have worked is to 6 to 8 months. So that's the game changer. So that's why now the industry is really moving towards this solution as the new tool in their toolbox. And yeah, it's a very exciting moment for us. Maybe I can talk a little bit about the Tiger. The Tiger is an acronym for what we do. We do target identification, we do guide design, and we do entry in the cell, and finally regeneration. We have all these. We have technologies developed in all these aspects of the editing process, and as I was saying, we are getting a lot of efficiency in the population. So in protoplast population, we just check by NGS how many of the protoplasts contain an edit, and we have 40% in a protoplast assay, which you know that many of the protoplasts are not viable. So actually, I think we are reaching really higher efficiency, which allows us later on not to have selection upon the regeneration. So actually, we do not need something there to keep track of what's happening on the editing. We just sequence, and we found at least in a few plants, we know that which ones have already has the edit. And the type of edits that we get with MAT7 are slightly different, but that you get from Cas9 or Cas12. We have these indels here, but they are a little bit longer than the ones that you see with other nucleases. But basically, what you have is an indel that hopefully sits down in the coding region of your gene of interest, and you have a proper knockout. The other aspect that we've been working is developing technologies for recalcitrant crops. So in the case that not all the plants actually can go through protoplast and go back and regenerate into full plant cells. So we have now developing protocols through collaborations and through IP portfolio that we are developing ourselves to, for example, encapsulating the editing machinery in particular nanoparticles with our formulations, different formulations for different species. And we managed to penetrate the cell walls and actually deliver the machinery there. And we can see here on the left, you can see with a nuclear localization signal that we are able to introduce the fluorescent marker not only in the cells, but also in the nucleus. And here on the right, you have just an assay to show that when we introduce the editing machinery, we actually have editing happening, MAT7 happening in the target of interest. So that's very promising, because that will allow us to move. It's a transgene-free approach. We do not integrate anything, but we can try to get to all the crops that right now are even recalcitrant for regeneration. And the last thing, as I was saying before, in the case of the protoplast, we have our technologies developed to not only to make single cell regeneration, so you can go up to this amount of dilution of the protoplast, and in the media that we provide, they're able to come back with clumps of cells that becomes homogeneous for the edit that you have, and they can become plantless later on. That can be moved. These clumps can be moved automatically with a robot into these plates. These plates contain only one individual coming from one single cell, so you know that there's a homogeneous background there, and they can grow. You can test for NGS to find out which ones contain the edit of interest. You select the ones, and then you put them back into the plates and grow them in the shooter-inducing media, and you end up with the plants that you can send to the customer with the genetic background completely homogeneous with the edit of interest. So all these things are happening. This is already, technology is possible, and we're just waiting for what can we do with it. This is another example, just briefly, about what you can do. An example of one thing that using conventional breeding will take years and years and years of crosses. Here, in just basically in one experiment, we just did it. So this is Nicotiana tabacum, it's allotetraploid. We were asked to knock out one gene family, 3 genes, all of them containing in the exon 1 a relatively conserved region. So we designed guides for MAT7, and we protoplast them and checked how many of these protoplast contains edits for the 2 guides that we designed. They were 150 base pairs apart. And we found the edits efficiencies around 30% or 20%. The efficiency of the guide depends a little bit on the guides, but this is the typical efficiencies that we can see. And we found out that 12 alleles were already edited in 3% of the protoplast. So that already gives you a feeling that how many plants do you need to scan to find plants containing the 12 alleles knocked out? Not many, isn't it? But that's the point. So with NGS, you can test your protoplast and find out how many are available. But the second part is that because these two guides were 150 base pairs apart, we could, using just a nested PCR, we can find out which ones contain a shift in the band, suggesting that there was already the two guides were editing, and actually you have a gap of 150 base pairs. We found out that 30% already were in one or more alleles. Already we found the shift, but already in 0.6%, we have the 12 alleles already shifted to this side. So now you see how many plants you need to screen again to find that all your 12 alleles in one round of editing in just a few months are ready for product development. I think that's how technology has advanced really, really fast. We have a technology in place that can give you wonderful opportunities just ahead. So now in this forum, I think a little bit of controversy is about, so what are we waiting for? Because many other countries, Sigrid was mentioning, our clients are not in Europe. This is the red there. Where are our clients? Our clients in South America, North America, in Japan. Now we have in Asia, we have now many clients. And that's what they are asking, because many of the products are exclusively for those markets, and they're like, okay, let's edit, no problem. But why are we waiting? All this technology that has been developed in Europe with European money, with all the European minds, is actually being used for the benefit of other countries. That doesn't make any sense whatsoever. But anyway, that's how it is right now. And maybe going back to Jorge, we at the industry, we have not so, how do you say that? Yeah, we do not see the signs being there. I mean, we see, of course, these flagships to change the way we are growing the food, addressing these societal changes. Yeah, and of course, these big sentences. Yeah, the RII are the key drivers in accelerating the transition to sustainable, healthy, and inclusive food systems from primary production to consumption. Wonderful. You look at the farm to fork, looks like the way to go. And I fully agree with that. I think all the principles are there. And if you look at the European Green Deal, wow, that's the way. I think the future is based on that. The question is, which tools the farmers in Europe have to actually apply these goals? Because the goals are there, but the tools are not there. It doesn't make much sense. And if you look at, for example, the word cloud, it's just a word cloud based on in the Horizon 2021-22. So for the new grants, the new R&D programs that there are there, 180 R&D programs that they're going to be funded in the coming time, only in the cluster 6 of food, bioeconomy, natural resources, agriculture, and environment. Do you see what is missing? Of course, nothing about CRISPR, nothing about innovation, nothing about the new technologies that will provide the farmer or the breeding companies the tools to actually develop the things. So we are defenseless. Actually, just to be completely honest, there is just one that talks about the new genomic techniques, but it's just to find out the benefits and risks about using or not. So it's really not about what needs to be done to develop the technology, to use the technology. So there are no promising signs in what is coming. So no doubt that this the plot I have, of course, is we're completely outcompeted by China, United States, by everybody else. Europe will be at the vanguard of at the rear of the innovation train, because we are not going to produce basically what the society is asking for. So other places where these technologies are actually the maps you see in green, all of them are adopting them now. They are using it now. Now it's in the commercial phase. So we are really, really lagging behind. So my final remarks is that, in one way, the CRISPR technology is mature enough to transform agriculture. The technology is there, the possibilities are there. So this is not so far away from actually being done in the coming months. And introduce breeding innovations in a very fast, accurate, and safe manner. We know that. We have a body of literature and science behind this. We are not inventing anything. We're just relying on standing on the giants of shoulders of giants. But these applications requires continuous method development. If Jorge doesn't have funding, how he's going to develop these things? If companies like us do have to move to the US because here we do not have the support for it. We will go to other places. So we will lag behind. The brain drain will be immediate. So it's a matter of time unless we reverse the situation. Just to put a little bit of also the problem is that it's impossible to trace. So the control and enforcement legislation will be impossible. Again, regulation in which all the parties are involved. That's the key. And just a couple of sentences coming from the last EU Agri Committee that I found particularly revealing how also within the EU there is this voice, this roar to change things. And I think they're right. I think there is a gap between the farm to fork and Green Deal ambitions and the reality on the ground. This gap is a very important one. And there are not enough tools to ensure the primary sector achieve the necessary technological transition. And we need to provide that. And this is about not the deregulation, as it is, but a control and tight regulation that all the parties are involved. And finally, I love this one. The problem is what will be the final outcome of this is that at the end, the EU risks to become an agricultural museum. And with that, I would like to thank everybody for your attention. I'm happy to answer any of your questions.